Let's try another. Let's try another. I'm going to eventually have you, I'm not going to fill this entire table out this time, but let's at least talk about the rule. Okay, so for number one, we were talking about meters to centimeters, if you couldn't tell. Meters to centimeters. I should have mentioned that. I didn't. So every meter is worth 100 centimeters, and the prefix centa means 100. That's why we have a penny is often called a cent. It's 1 out of 100 for a dollar. Let's take a look at number two, where we're going to break down centimeters into even smaller measurements, into millimeters. So let's take a look. Again, all we need to do is go to our first imaginary where the decimal would be. 1 is the same as 1.0. So you can put a decimal there if you want. And take a look at how many spots does our decimal move over. So in order to have that 0, that means we would have to move it one spot, because we said every time we have an empty cloud, a 0 has to go in it. So in this case, our decimal moved one spot to the right. And if we're moving to the right, do you remember whether that's multiplication or division? To the right is in fact multiplication. So we're multiplying by 10. And how many place values did we move over? Just one. So 10 to the first power, which is also known as just 10. You can, for 10 to the first power, you can just say 10, because it just means times 10 by itself. And you might be saying, why can't we just always say times 10 and then do the math? That works for some. For instance, we know 3 times 10 is 30, so you'd be like, oh, fine. But where understanding the powers rule comes into play is on one like 4.7. If I asked you what's 4.7 times 10, it's understandable if you're like, I don't know that offhand. That's where our rule comes into play, our powers rule. We know it's multiplication, so it means our decimal needs to move to the right. And we know the exponent in this case is 1. So how many places to the right should our decimal move? Just once. So take that 4.7, take that little decimal point, move them one spot to the right, and suddenly we know that 4.7 times 10 equals 47. Now let's take a look at what happens when we need to go in the opposite direction. So here we have the out already listed for us, 50, and again, when there's no decimal, we can just imagine there's 1 right at the end. 50 is the same as 50.0. So the trick here for the 50 is now we need to reverse our action, because we need to go back to what we had at the end. And if we're going right 1 to get our answer, that means to reverse it, we're going to go backward. So if we went right 1, now to get our in, we're going to go back 1, which would be almost like dividing by a power of 10. So we're going to take this imaginary 0, go back 1, put them in reverse, which means the in must have been 5.0. And you can test and check by taking this 5.0 and saying, all right, well, if I applied the rule to them, times 10 to the first power, would we end up with 50 if we moved them one spot to the right, just like a rule says? And we would. So this one would work. Okay. Now I keep on looking. They keep on kind of throwing loops at you. I don't know, challenging you. I said I wasn't going to do this one, but actually it turns out there's a lot of good learning moments here. We take a look at 5 here. So the 5 starts with a decimal point, imaginary 1 here. And we need to go back 1 spot. So I want you to decide what's going to happen on the in, since again, this is going to be another reverse. They're giving us the answer already, the out, so we need to reverse it. And actually, that one's not as tricky as I thought. I think you'll be able to pull that one off, so maybe I won't answer that one for you. I'll let you tackle that. Maybe what I'll do in the interim is we'll move on to number 3, and we'll at least talk about the rule. So here, we're starting with a very large number. We're going from grams to kilograms. And you have to do the same thing. Again, our imaginary decimal is going to be right at the end, and you need to recognize what's happening to him. Where is he ending up? And in this case, he's ending up right after the 1. There's no other zeros. The zeros are eliminated. So how did we get from here to the 1? How many places did that decimal have to move? And you can walk yourself through it. 1, 2, 3. He moved 3 places. So that means our exponent's going to be 3, 10 to the 3rd power. The next question is going to be, what direction did that decimal point move? He started here, and he ended here. And here's my right hand, here's my left. So he went to the left. What's it mean if it goes to the left? Is that going to be a multiplication problem or division? Well, so far we've only gone right, and right has meant multiply. So left must mean divide. This is a handful, guys. I wouldn't doubt if you're trying this at home and you're confused, it's okay, because this is probably the most interesting one we've had yet. I would recommend going back and rewatching certain parts and double checking of what's going on. It's always easy for someone who knows what's happening to describe it. The question is, can I describe it in a way for you to understand? Which sometimes is easier than other times. I'm going to flip over for a moment to show you another section, if this is going well. I wanted to throw some conversions at you, just so you know if you get to these problems. So first, I'm going to skip down to number 2, because they're talking about converting milliliters to liters. I'm going to help you out real quick. If you decide to tackle this one, I'm going to tell you 1 liter is equal to 1 milliliter. Oh my gosh, that wouldn't make sense. Sorry. Losing my mind. 1,000 milliliters. So you can use the same rule. You can take a look, how many place values would we need to move to get to 1,000? And that will tell you your rule for converting liters to milliliters. And also, when we're talking about meters and kilometers, or kilometers, which is going to be the basis for number 3, 1 K, or 1 kilometer, is equal to 1,000 meters. Like, you know, like a meter stick, 1,000 of those. And do you notice what I meant when I said the metric system always has a pattern? Everything's a power of 10, everything's super clean. You know, every single conversion is like 1 equals 1,000, or 1 of these equals 100 of these, or it's all powers of 10. It's no like, hey, 12 inches equals 1 foot, and 5,280 feet equals 1 mile. That's just straight memorization, and there's no real rhyme or reason to it. You might be able to tell with how clean everything is with our metric conversions. This is why the metric system is the preferred system of use for scientists and anything really involving serious data, with some exceptions. I personally prefer the imperial system because I'm an American and this is where I grew up and that's what I know. But the metric system undoubtedly is a little easier to tackle when we're talking conversions. So that's the story on that, and that was a long one, longest one yet. If you made it all the way through, congratulations, you're awesome.